In this video we're going to be tying up a few loose ends regarding the derivation of the Jacobi accessory equation. So that's the accessory equation written there. Now it can be rewritten in this form if we replace a factor of it by g, just as written there. Right, now if u1 and u2 are independent solutions, then we can rewrite it in the following format. Okay, so you'll see that equation that I've got here in front of you in the book as well. That's equation number 1 here. So that can be rewritten in the following form because we're going to have a repeated use of the product rule. So it's like the product of 3 different functions. So it allows us to bring the u1 and u2 inside the differential. I've done that in a previous video. Okay, I'll also put maybe that in a snippet section separately. So that's going to give us equation here, equation number 2 that you see, where b is a constant. Okay, now we made an assumption before when we derived this Jacobi accessory equation. Now you'd have to go back to the video, so you can click on that link here just above and you'll be able to take you into the video so you can see this, the derivation of Jacobi accessory equation. But we derived that equation there, we got to that point there and we made an assumption that we could get rid of the part of the integration by parts that's no longer within the integral sign. So we assumed that the value of t of a and t of b equals 0, and we ignored it. But that wasn't the whole story. There was a factor of this, that eta squared u derived upon u upon t squared from a to b, and if that with the possibility of having a repeated root as shown there, then we could be in the position where that u of a would tend towards 0 and the whole thing would tend off towards infinity. Okay, so we wanted to highlight this and prove that it wasn't possible to have a double root. So we used equation number 2 above, which is just rewritten in order to prove that that is the case. So except for a special case where f11 tends to infinity, so we'll just ignore that. And if the f1 doesn't tend to infinity, then we can see that the value of u1 and du1 of x, and also u2 du2 by dx can't both tend towards 0 at once. So it means that then that it isn't possible for that to have a repeated root. Okay. So just to finish off with, we're going to show that if we were to take the above equation, we can rewrite it using the quotient rule, and we're going to have this formula here where we have d by dx u1 upon u2 equals b upon f11 upon u2 squared. So it means that the value of f11 from that must have the same sign at all points on AB. So we know that because that's part of the derivation of the Jacobi slash the Legendre test. So if that's the case, then we know that d by dx u1 upon u2 has to have the same sign for all points on AB. So it means that u1 upon u2 is either strictly increasing or strictly decreasing. But we have actually showed earlier that u1 and u2 must have the same values at conjugate points. So there seems to be a contradiction here, but there's not actually any contradiction because we do know that the equations that we derived in order to find the abscissa of the conjugate points do actually have jump discontinuities. So for example, when we looked at the abscissa of the catenary has jump discontinuity, so it means that we can have multiple values for each value of our independent variable x. In the same way that a tan function is continually increasing, you can have multiple values of the same value x, but it's strictly increasing. Okay, thank you for listening. Hope you enjoyed that, and I'll catch you on the next video. This is a quick demonstration. What we have here is the catenary, and the dotted curve here is the equation of the x coordinates of the conjugate points of that catenary. So for example, if I was to shift this along, you'll see that the x coordinate here is given by the point where this curve cuts the x-axis, and also the x coordinate of that conjugate point is given by the point where this point here cuts the axis. Now what we were going to show, and we show near the end of this video, is that I mentioned that the equation for the abscissa of the conjugate points has got a jump discontinuity, okay, and you'll see this cropping up in other examples. So for this example in the catenary, you can see there's the jump there, okay, so there's a jump there. So it means that the equation then for this abscissa of the catenary is either strictly increasing or strictly decreasing. Okay, so that's all. It's just an added extra that will tie into what's on at the end of the video. Okay, thank you.